Welcome back, everyone. I'm Jordan Giesige, and this is The Limiting Factor. Donut Lab claims to have a battery that achieves a whopping 400 watt-hours per kilogram of energy density, charges in 5 minutes, lasts for 100,000 cycles, uses abundant non-toxic materials, can maintain performance at extremely low temperatures, is safe at very abusive temperatures, and is lower cost than lithium-ion batteries. The question is the donut battery real? In my view, it's not, and in today's video, I'm going to walk you through why that's the case from a first principles physics perspective and from a more pragmatic manufacturing perspective. Before we begin, a special thanks to my Patreon supporters, YouTube members, and Twitter subscribers, as well as Rebellionaire.com. They specialize in helping investors manage concentrated positions. Rebellionaire can help with covered calls, risk management, and creating a money master plan from your financial first principles. First, what do I mean by, is the donut battery real? I don't doubt that Donut does have some type of battery that they've been developing. However, when or if that battery hits the market, I don't expect it to hit all the specs they've been advertising. It's possible they can make a battery that can hit 400 watt-hours per kilogram, and it would be impressive to hit that energy density while charging in 5 minutes. But to hit a third spec, such as 100,000 cycles, it starts to stretch credulity. Then, to hit a fourth spec, such as cost parity with lithium-ion, it starts to enter fantasy land. And that's before touching on the rest of Donut's incredible claims. I'd love for Fantasyland to exist, and I will happily eat my words if I end up being wrong. But the odds are very much against Donut Lab here. Let's dig into why that is. On screen is what's called a Ragone plot. Named after American engineer David Ragone, who first introduced this type of graph in the 1960s. It compares the energy versus power density of energy storage technologies. This specific Ragone plot compares lithium-ion, sodium-ion, lithium titanate, solid-state lithium metal, and electrochemical capacitors. I picked it because some people are suggesting the donut battery is not actually a battery, but some type of advanced electrochemical supercapacitor like a pseudocapacitor or carbon nanotube-based capacitor. But here's the rub. If we place the donut battery on the Ragone plot with a pink star, we can see that it's far beyond the performance of established batteries and supercapacitors. For some historical perspective, the last time we saw a leap in battery technology anywhere near that transformative in any dimension was in the 1990s when lithium-ion batteries hit the market. However, that advancement was initially just along one dimension, energy density, but not in others like cycle life or cost. Lithium-ion batteries in the 1990s had no better cycle life than the alternatives and cost about 5 to 10 times as much. Donut, on the other hand, is claiming their batteries not only far outperform current lithium-ion batteries in terms of energy density, but on every other key spec and feature. If that happened, it would be unprecedented in the history of energy storage technology, going back to the first commercial rechargeable cell, the lead-acid battery, in 1859. So if the donut battery is real, it would become one of the hottest technologies in the world, and Donut Lab would become a multi-trillion-dollar company. They would swallow up the EV market, the battery storage market, and light the fire on a new era of electric flight. As a reminder, we have seen hype like this before in the battery industry. The instance I'm most familiar with is QuantumScape, which I did an entire video series on. In 2020, QuantumScape claimed that compared to lithium-ion, their battery would provide 82% more range, charge 33% faster, and have longer cycle life, all while eventually costing 17% less. Then, to unveil their battery, they held a Zoom call with notable figures in the battery world, including Nobel laureate Stan Whittingham, who helped develop the first lithium-ion battery. He backed up QuantumScape's claims, saying that he'd not seen data this good anywhere else, and that he thought it was a real breakthrough. 6 years later, we're still waiting on the QuantumScape battery. The sample batteries look promising, but they fall short of the original specs, and there are now conventional liquid electrolyte battery cells that can match its performance. All this isn't to bash QuantumScape, because from a technical perspective, what they're achieving is still impressive, but to point out that there's marketing and then there's a final delivered product. Why does the final delivered product for miracle batteries always come up short? Because battery startups are incentivized to oversell lab-scale results to gain funding and attention, and because they're genuinely excited about their vision and solving the commercialization challenges, and that excitement spills into over-optimism. But Donut Labs' claims are on an entirely different level. While QuantumScape and hundreds of other startups started off with lab-scale cells and claimed they'd made good to great advancements over lithium-ion batteries on several specs, Donut Lab is claiming to have obliterated every metric and are already able to produce batteries for commercial customers at high volumes. Let's dig a little deeper into the physics behind the Ragone plot, because it explains why we don't see any technologies on the Ragone plot that are both extremely high power density and extremely high energy density. I'll start with cycle life versus energy density to build a base of understanding, and then come back to the power versus energy density of the Ragone plot. The way that a lithium-ion battery works is that during charging, lithium ions and electrons are pushed from the cathode to the anode, and when it's discharged, the lithium ions and electrons return from the anode to the cathode. There are two ways to increase the energy density of the battery cell. The first is to use cathode and anode materials that have a higher voltage difference between them. That can cause problems because it makes the battery cell more reactive and reduces its cycle life. The second way to increase the energy density is to increase the proportion of energy-storing lithium atoms to structural atoms in the cathode and anode material, or to force more of the lithium ions out of the cathode when the battery is charged. But both of those options can also cause cycle life issues. That's because increasing the proportion of energy storing to structural atoms means the battery becomes less durable, and if the cathode gives up too many of its lithium ions during charging, the cathode crystal layers can collapse. Those, amongst other factors, set up an inherent conflict between cycle life and energy density, and it's the reason why lower energy density chemistries tend to have longer cycle life. Only so many atoms can fit in a given mass or volume within a battery cell that are devoted to structure or energy storage. The more that are devoted to structure, the longer the battery cell will last. And the more that are devoted to storing energy, the higher the energy density will be. So it's hard to achieve both. A similar dynamic exists between energy density and power density. For example, one way to increase the charge and discharge speed of the battery cell is to shorten the average ionic distance and therefore reduce the resistance between the cathode and anode by making them thinner. But with less cathode and anode material as a proportion of inactive material like current collectors, the battery cell stores less energy. I'll give more examples in a moment when we cover supercapacitors. So what are the ways around the first principles conflicts between energy density, power density, and cycle life? I see two broad options. First, by understanding every material that goes into a battery at a deep level through decades of research and manufacturing experience to squeeze more out of every atom through better chemistry and engineering. That can include anything from tweaking the recipe for cooking the cathode material to finding the perfect ratio of conductive carbon to binder to active material in the electrodes. Needless to say, the drawback of this option is that it's a slow and incremental process. but it's been proven to be effective over the past 30 years. Second, by replacing some of the cathode or anode material with extremely durable materials like carbon nanotubes. However, the highly ordered structure of those materials means they're typically expensive to manufacture, which increases the cost of the battery cell. That's often feasible in tiny amounts to provide a moderate increase in performance for a small increase in cost, but higher performance requires exponentially more high-cost material. So, moving to much higher energy densities with carbon nanotubes or even silicon nanowires is possible, but only for niche market segments that can afford the price tag. For example, the batteries that Amprius is marketing towards military applications can fetch up to $3,000 per kilowatt hour, which is about 30 times the cost of EV batteries. Now that we've covered batteries, what about supercapacitors, or supercaps for short? There are three major types of supercaps that fall under the umbrella of electrochemical capacitors: electric double-layer capacitors, or EDLCs, pseudocapacitors, and hybrid capacitors. In the simplest of terms, EDLCs store energy with static electricity. The limiting factor for how much static electricity can be stored is the surface area within the EDLC, which greatly limits their energy density. That's as opposed to batteries, which store their energy with chemical reactions and the full volume of the material in 3D, which gives them around 20 to 30 times more energy density than an EDLC. However, unlike batteries, EDLCs don't have to move much ionic mass around to store energy. Moving mass around causes degradation and is slow. That makes EDLCs much more durable than a lithium-ion battery, lasting hundreds of thousands of cycles, and allows them to charge or discharge within seconds. Pseudocapacitors, on the other hand, operate in ways that are similar to both a battery and an EDLC. Like a battery, pseudocapacitors store energy through chemical reactions, but instead of shuttling ions back and forth between the electrodes, the chemical reactions remain localized between the electrolyte and electrodes. Due to the fact that chemical reactions are being used to store the energy instead of static electricity, pseudocapacitors typically have about 2 to 5 times higher energy density than an EDLC. But batteries still have an energy density that's around 10 times greater than pseudocapacitors. That's because although pseudocapacitors do use chemical reactions to store energy like a battery, it's done through surface or shallow reactions that don't engage the full material bulk, even in intercalating versions. That is, again, the energy density of pseudocapacitors is mostly limited by their surface area. On the flip side, because they don't have to move much ionic mass to charge and discharge, they can achieve high charge and discharge rates. Not as fast as an EDLC, because they still have to react and move more mass around, but still quite rapid in the range of seconds to minutes. As for hybrid capacitors, they're just the result of different combinations of EDLCs, pseudocapacitors, and batteries. That means their energy density, power density, and cycle life can run the gamut depending on what combination is used. But they still have the same benefits and limitations as the battery and supercap technology that they're derived from. Combining technologies doesn't compound benefits, but rather just broadens the set of trade-off decisions. The key takeaway here is that for supercaps, just like batteries, every technical spec is in conflict with every other spec. So for each spec that Donut claims they've hit a technical home run on, it compounds the unlikelihood that they'll actually deliver. I know at this point that many people will want me to do a technical deep dive on what I think Donut's actual technology is, as many people have done. But from my perspective, there's so little information out there that all it would do is add noise rather than signal. Instead, for this video, I thought it better to give a small masterclass on the deeper fundamental issues with the claims that Donut is making, which I'm hoping will prove to be more educational while also cutting through the noise. If you are interested in analyses of speculation on what Donut Labs battery is, I'd say the best summaries I've seen are by Zeroth and Tom Boticher, and I'll link those videos in the description. With the physics out of the way, let's move on to the manufacturing challenges. The only way to manufacture batteries as cheap or cheaper than lithium-ion batteries is to use materials that are dirt cheap. But even then, it's not guaranteed. For example, despite sodium-ion batteries using cheaper and more plentiful materials than LFP batteries, it's still going to take the sodium-ion industry years to reach the colossal scales necessary to compete with lithium-ion batteries on a cost basis. The odds of Donut finding a set of materials for their battery that are both cheaper than sodium-ion and also much higher performance would be difficult to say the least. That's because not only would the raw materials have to be cheap, but also the string of processes required to turn the raw materials into high-purity, highly structured battery-grade materials. Exotic materials that have been suggested for the Donut battery, such as solid-state electrolytes or carbon nanotubes, would blow out the cost budget compared to lithium-ion batteries, even with cheap raw materials, because they rely on slow, low-volume production processes. On that note, in order to hit their advertised specs, the Donut battery will need to use a novel cathode, anode, and electrolyte and/or separator, because nothing exists that I'm aware of that could hit their performance claims. Novel materials mean Donut would have needed to not only set up manufacturing for the cells and pack for their battery, but also manufacturing for each novel subcomponent that goes into the battery cells, which would have involved years of effort to develop manufacturing processes, quality control systems, and supply chains for. For perspective, it's taken several years for CATL to build a basic industrial supply chain for sodium-ion batteries, and that's despite sodium-ion batteries using almost all of the same production equipment or even the same materials as lithium-ion batteries through most of the supply chain. Donut Lab, on the other hand, would basically be starting from scratch to build out their industrial base, and doing it with what would likely be cutting-edge materials and processes rather than stock standard processes. Lastly, besides cheap materials, producing batteries requires a highly reliable, high-precision, high-throughput process to coat the electrode foils with active material. Donut Lab is allegedly using some type of screen printing technique to coat their electrodes, but companies like CATL and Tesla chose deposition techniques like wet slurry coating and dry coating for a reason. They're faster than screen printing by at minimum 2 times, but usually more like 10 times. What all this means is that even if Donut was by some miracle able to hit the specs they've advertised, a second miracle would be required to hit a manufacturing cost that's the same or lower than lithium-ion batteries right out of the gate, if ever. In summary, both the physics and industrial realities are that Donut's battery is unlikely to exist as advertised. Although batteries just look like dumb cans, they're high-technology, multi-scale, multi-physics systems that have been optimized over the course of decades. As a result, they're brutally well-organized collections of matter and energy, produced at gargantuan volumes that have baked in hundreds of trade-off decisions learned painfully and methodically by tens of thousands of scientists and engineers. So it's never happened that any new battery technology has resulted in massively improved performance in one spec without negatively affecting the others, making the odds of massively improved performance on every spec at once dismal to say the least. And then on top of that, it's also unheard of for a new company to become a premium, high-volume manufacturer of battery cells right out of the gate. It usually takes about 5 years of manufacturing hell. That's because simply making a battery cell is hard, even if it's stock standard lithium-ion, let alone building multiple new industries and processes to serve an entirely new chemistry. With all that in mind, I'd say the odds of Donut's battery existing as advertised and produced at volume are about the same as some other random company without any extensive and clear track record of research and patents claiming out of the blue that it's about to start manufacturing room temperature superconductors at volume for the price of fridge magnets. In fact, the odds of Donut's battery existing are probably lower because a high-temperature superconductor will likely only involve one new material, not several. If it does turn out I'm wrong, and the Donut Lab battery does deliver on every spec and feature, or even at least half of them, you can be rest assured I'll do an entire video series on it, because it would be a major breakthrough. But I'm not holding my breath. As always, please consider supporting the channel with the links in the description, which now also includes a referral link for Signature Solar. If you use that link to purchase home battery or solar equipment, it nets me a small percent-based credit, but that can add up on a large purchase and it really helps the channel. On that note, a special thanks to my YouTube members, ex-subscribers, and all the other patrons listed in the credits. I appreciate all of your support, and thanks for tuning in.